Student. No one home. Yellow signal, blue signal. Oh, they are not happy. Now they are much happier. Okay, what's going on here? In multiple instances. I have quite large schematics here, isn't it? All kind of different stuff. Make it more. Why it's all here? So I have a lot of different objects here. I can start from this corner. Here, in this corner, I have this nice red coil. It's sensitive. Capacitor, divider, this funny neon, and this electron tube. Ground grid. There we go. Ooh, 250 volts. Variable capacitor. capacitor. Output divider, and also I have this neon lamp as a limiter. And this is my signal 1. So, any idea what can it be? This coil, this capacitor, neon lamp, voltage divider, and electron tube. This is coil LA and capacitor CA. Today I have a lot of objects on my table. I'm starting to discuss this column. Here is schematics. Of this coil. I have nice red coil. This one, it's a transformer. Its secondary winding is connected to the grid of my electron lamp. I have this nice variable condenser. This one. Yeah, 9055.
This yellow input. Blue
Yellow, yes.
What about red?
We will discuss it. First, I started with yellow one. What it can be, the schematics. It's okay, it's visible now. Big and large. We saw something, two lectures before, where I spoke on systems with feedback. It's an amplifier loaded with resonance circuit and with positive feedback. What is it?
Resonance circuit?
All together. Amplifier loaded with resonant circuit and with positive feedback. Generator of harmonic signal. In case of positive feedback, such network, linear amplifier with positive feedback and resonant load is a generator of harmonic signal. Here it is. Here I can show it on a second scope. Here is my harmonic signal. This circuit works as a generator of harmonic signal, or near harmonic. You can see small distortion. Come on! Small distortion there. Its frequency 550 kilohertz approximately. Fine. I have one circuit. My second circuit is this black device. Okay, oh. My black device is a bit more complicated. Here is my schematic of my black device. What can we see here? It has two resonant circuits. Idea when you have only one selective circuit in your generator and it's coupled with load resistance will decrease its quality. This means what frequency will be not so stable. To increase quality of signal, one of the way is to use, how to say, in sequence pair of resonant circuit. They should be adjusted to same frequency. So what's here? This part here is positive return. So this part sets and generation frequency. Load also resonant. It's like connected to selective circuits in serious way. This reduce, how to say, this narrows real bandpass, real width of band of this bandpass system, and increases quality of signal. You can see yellow one. See the small disturbances in yellow one. Yellow one resonance circuit. Blue one 2. It has a better quality. It's more stable. Now, is this part clear? What's on my table? One generator of harmonic signal, two generators of harmonic signal. What I'm trying to do, what I'm trying to show. I would like to show idea. What if here is, let's say, S1, here is my S2, yeah? What if I say I will sum them? What will happen if I use both together? Yeah. Here is, this scope is repeating blue one. a singing bowl. Wait. Here. Which hunters are on the way? Strange, isn't it? You know what? You see frequency? 547. It's far outside of human hearing range.
Do we feel anything, Professor, when we are doing like that?
Sorry?
Do we feel anything while we are
No. I can also take my fairy roll. This thing is insulated. This point will It's kind of bad magic, isn't it?
Yeah.
But
How the sound waves are generated?
yeah. What's going on? 547 and 547. What's going on? I need to switch my scope. Wait a second, I will switch to another point. I think this one. The yellow line is a sum of two signals. I can show it in this scale, but it's watch it in this compressed. What happens? I have one signal as cosine omega 1 time. I can represent it as a rotating vector. Its magnitude will be magnitude of my first signal, and it rotates with the speed omega 1. I'm adding a second one. First one is from this circuit. Second one from the black. So this one is yellow. And here is my blue signal. And it rotates with the speed. Okay, it rotates with the speed omega 2. Fine? Fine. Now I can draw a line. It's S1 plus S2. Yes? Yeah. Maybe. I'm not happy. Maybe like this. Like this. And here is my circle. I'm interested in this angle. That. Why am I interested in this angle? I'm interested in this angle. This one represents first signal. This one represents second signal. I don't know, where's the yellow chalk? Can I write a mass for this vector? I can. So, this vector will be square root S max 1 square plus S max 2 square minus double S max 1 S max 2 cosine theta. Is it correct? Cosine, theorem of cosine.
Yeah.
Yeah. But what is theta here? If one is rotated with speed omega and second one and second is omega 2, this angle, what it will be? Omega 1 multiplied by time, yeah? So actually, I'm seeing something where driving force is cosine of omega 1 minus omega 2 or omega 1 prime. In case, but I have a square root of it. In case of the large signal, I will see something like this. If they are equal, at this, it's in case when signal magnitudes are equal, at some point output will fall to 0. In case there is large difference between them, I will get something like this. I will get something like this. is a cosine. But what about frequencies? And here is interesting moment. Fourier transform of such signal yields an interesting picture. 1 second, I will. Where is my Fourier? Oh, here it is. Here is my oops, here is case when signal magnitudes, signal frequencies are very close and central frequency, I hope you can see the red line, is for 452. Yeah, I hope you can see it. Now, if now frequencies are equal, what I'm doing? I'm adding a capacitance to the resonant counter of the first signal. This changes its frequency. And you see what emerges? See these two side lines? What can be the frequency? Plus delta omega, minus delta omega. Picture what I'm getting is a very typical to the signals of variable amplitude. I see central at my omega 0. It's a frequency when they are equal. And this one with plus delta omega. And second one is delta omega. Who's calling and why? I will kill them all. I will slice them in. Yeah. И во сколько? Ну, у меня я вот в 2 закончу.
No, I will. They are planning to play football on Sunday. People playing, he playing, and some other. No.
You cannot say this option. There is no such kind of variant in the answer sheet. There is only one choice. Yes, yes I can.
Only the choice?
Yes. There's no other choice. It's mandatory. Oh. Got it.
If you try open your trigonometry book, try to open your trigonometry book, you will find the trigonometry for sum of cosines. And you will see plus and alpha plus by alpha minus by. Here it is plus delta omega minus delta omega. You see spectrum? The outer line is a cosine of, in my case, it's something close to cosine of omega 1 minus omega. And inside, feeling. What's inside? I'm in the wrong. What's inside? Bit wobbling, but it's a cosine of 5 to 6. Now, you know what I like to do? I would like to get this borderline I would like to separate the somehow get this outer line. What can I do? I can apply detector. I can introduce such circuit. I will take this one as a second signal. I would like to get magnitude of my hits. Why? There is always not enough maybe I'll it's a magnitude of my signal. See the frequency.
Is it magnitude of your first signal or second signal?
Blue line achieved as a magnitude of yellow.
Like, which means it is amplitude. You say amplitude, yeah?
Yeah.
Amplitude of +7, which means
But blue line is a how to say amplitude of yellow. And it's It's a low frequency signal I looked for. It's a different signal of difference. It's a near harmonic. It's not ideal. You can see it's not very harmonic, but it's signal with the frequency. With differential its frequency is omega 1 minus omega. Actually, it's an absolute value.
So, is omega 1 and omega 2 difference more big? The more harmonic?
No, not harmonic, the higher will be frequency of difference. This one moment.
I'm talking about this blue line.
Yeah, blue line, it's near harmonic. It's not ideal because
More difference big, more near to harmonic.
the bigger difference, the higher frequency. Distortion, it's not no linearity. See, at low difference, I have theoretically higher distortion. Because my circuits are not ideal. But here something close to harmonic. This demo, what's changed? Capacity. The higher capacity of the contact, the higher inertia, lower frequency. It's no difference. Which of the circuits shifts down? Anyway, I will see increase in output frequency because they have a difference place. Hundred years ago, this coil was sold as a more immune to output, to outer fields, because it's toroidal. See, not 100% immune, but it's better than cylindrical.
Such kind of code is used in military base?
Yeah, possible. This one, exactly this one, I believe, it was a set. Wait 1 second, I can show the second one. It was sold, yeah, really 100 years ago for homemade receivers. Here's the second one. It was a basis my work. Only coil was sold. Make your receiver.
It looks good.
It looks good, yeah. That's why I determined what it's. I can show to my online viewers here. Old toroidal coil. What good with toroidal coil? Magnetic field closes. Magnetic flux goes inside, so it's really less vulnerable to outer fields. In case of traditional cylindrical coil, magnetic flux goes like this, so it's more vulnerable to kind of disturbing influence. A coil with closed magnetic system.
So when you get time, you are making some kind of coils.
Yeah, it's all no. The coil itself is original. It's
Okay. No, I was asking about the base. And
yeah, basically it's my first trade was assembler of radio equipment and apparatus.
So most of the equipment over here is like collected by you.
all this is mine except the TV and this scope.
Professor, I have a small question about this sphere.
Yeah, it's actually it's hollow. It's a garden decor from LA.
Like right now, you are increasing frequency.
Yeah,
I'm
the interesting moment. I'm decreasing frequency. Wait 1 second. Where he is? Where are you? Oh! Here. I have this object. Capacitor disassembled. Capacitor, what can be? Disassembled. I can substitute here I have a balance, here capacitor. 1 second for online. Here, capacitor.
So this is stainless steel?
I'm not sure, maybe stainless, but I think it's just coating. They are sold as a garden decor, balls itself. Base is original from 50s. It's it's isolated base. Yeah, and this shows what I got it in 2 parts. This base was it was a set for physics class for schools, and ball it's a garden decoration. Only drilled, this socket soldered, and base attachment also. It's soldered inside. I got paid, I don't know, 5 euros, something like this. It looks nice. Why should I pay 100 for new one if I can make?
So it's been so many long years you have been collecting these ones.
Long. I started in 90s, so 30 years. It's not all. Now I have problem. I used all available space. Now I'm very selective on what I will take. Well, okay, what I'm trying to do. Watch, capacitor. Capacitance increases, frequency of the black generator decreases, but difference increases. In opposite, I can adjust. Here, 1 second, in some. Here is 0 in some position. Capacitance increases, frequency decreases, some increases. Opposite.
Professor, if we fully attach them together, it will say,
In theory, generator should stop, but I have a capacitor in between.
like, I mean, there's charges, and if we fully attach it, charge will like flow to each side, and
Yeah, but schematic.
and
If
service.
I am preventing short circuit, wait 1 second, I will draw schematics. It will explain. What my electron valve. capacitor, coil. This is to get output, the output, the part we are interested in. I have small capacitor, and now we have this capacitor. I have separation capacitor in series. If there will be no such capacitor, if here would be a voltage. I'm not trying to kill myself. It's kind of 100, like for something small. In one case, in case of both sources, it's a capacitance against ground. So I'm adding additional capacitance. This one is variable, so I can adjust zero difference between two generators. But if I introduce something here, it will change overall capacity of this contour, and frequency will shift. What can I do? It's kind of fun. The demo waste my... Oh! Yes, permeability of the book changes. Changes electrostatic conductivity of capacitor, meaning changes its inertia. And we see it as a difference in frequencies. Yes, yes, yes. I don't know. Maybe this one about relativity theory. No, relativity theory is not so effective. This one is weaker. Okay. Okay, it's a funny toy, but I would like to add bit theory here. This kind of baseline, let me switch you off, for such kind of tricks. This one belongs to Theremin. If you're interested, you can search for Theremin box. They are still produced in Japan. I don't know Japanese market. Somehow very they like this toy. But what I would like to do, I would like to show a bit of theory. Pair of theorems. I hope I have time. So we saw a demo on what? On mutual effects. Mutual effects of two signals. When we speak on mutual effects or interference or something like this, it's good for us to understand a couple of things. The first thing is so-called Parseval theorem. Idea. Let's say I have a signal and I can obtain its spectral function via Fourier transform of the signal. Let's assume I'm loading my signal with 1 ohm resistance. Where is my 1 ohm? Here, this is my 1 ohm resistance. It's a 1 ohm. So, I'm attaching my signal to my 1 ohm resistance. What will I get? Overall energy is integrated in infinity margins as, yes, because 1 ohm. Or I can write it in such a way, multiplied by 1 divided by double P, infinity to infinity, Gs from omega, a power omega time, d omega, d time. What I wrote in square parentheses. It's an inverse Fourier transform of the signal spectral function. I substituted one signal with its inverse Fourier transform. Now, if I change order of integrals here, I can write it in more, how to say, pleasant form. I can write it as 1 divided by double integrate from minus infinity to infinity. My spectrum function of my signal integrate infinity to infinity as a power of omega time. Yeah, I wrote it. But what I wrote? What's this? Looks like Fourier transform, yeah? But only here is missing, minus. It's a Fourier transform, so it will give me my signal spectral function, but with negative frequency. Or conjugation of my spectral function. Know what it means, conjugate? Huh? Who knows?
Like inverse
Function.
like for example, if some function f, it like how to say,
Simple.
Like conjugate complex or conjugate.
Yeah, it's for complex number. If I have some complex plus 1 a b, so my x is a plus b, its mirror or conjugate will be a minus b. It's like mirroring in complex plane. So here I'll get two. I will deal with two complex functions, being one being mirror of another. Not mirror, but mirrored. So I can write my energy minus infinity to infinity d time equals to 1 divided by double p, infinity to infinity, my signal spectral function multiplied by conjugation of my signal spectral function, d omega, or 1 divided by double p, infinity to infinity, square of absolute value of my spectrum function. Name of this is Parseval theorem. They are often go in pair with Rayleigh theorem, theorem of Rayleigh-Parseval, but this one is a Parseval theorem. On the basis of Parseval theorem, one thing is introduced. Here is a problem. When we deal with real high frequency, we don't see voltage or current, we see energy. Special value Ns as a function of frequency. It's called spectral density of signal. So it's a square 1 divided by p square of its spectral function absolute value square. It tells us what? It tells us distribution of signal energy by frequency. High frequency spectrum analysis to give watts or milliwatts or microwatts per hertz. Usually per megahertz or per gigahertz. They have a gigahertz scale. Oh, it's a spectral density. Okay. Now, what about two signals? Parseval theorem speaks on one signal. What about two? So I have one signal and two signals. And first spectral function is a result of Fourier transform of the first signal. Second spectral function is a result of Fourier transform of the second signal. What I'm looking for? I would like to know what about Fourier transform on S1 plus S2. I would like to know frequency characteristic of when they are acting together. Fourier transform is linear. So, I can expect what energy S1 plus S2 to 1 divided by double P, integrating in infinite margins, GS1 from frequency plus spectral function of my second signal square the omega. I can expect what my Parseval theorem will work in linear way because Fourier transform is linear. Now, what can I do with this one? Square of modulus. If there is, let's say, x plus y complex square, you can check it. You will have x plus y multiplied by x conjugated plus y conjugated. This knowledge allows me to write, to open all brackets and get, what will I get? I will get minus infinity to S1 square of time plus infinity is infinite S2 square of time plus double infinity to infinity S1 S equals to 1 divided by double P. What I'm writing here? Infinity to infinity GS1 conjugate as a function omega, the omega plus, in infinite margins GS2 from omega, GS2 conjugated from omega, the omega plus integrate in infinite margin GS1 GS2 conjugated plus GS1 conjugated GS2 conjugated the omega here. Yeah. Funny, is it funny? What do I see? I would like to compare this to this. What do I see? I see Parseval theorem. Meaning what these two are equal. I can compare this to this. And they are equal because it's a Parseval theorem. So this one and this one are equal. And I can write what is called Rayleigh theorem or theorem of interference. S1 S. What is this? Coupling or interference. It's an interference energy or mutual influence energy. Energy of interference. The It's a result of signal interference. Energy seen on 1 ohm resistance can be higher or lower than simple sum of two energies. And what is equal with 1 divided by 4p minus infinity to infinity gs1 from omega gs2 conjugated from omega plus gs1 conjugated gs2 not conjugated, and here the omega. Here is answer to interference ratio. Mutual energy. If this energy is not zero, how do we call light sources if they produce interference picture in physics? Coherent. If energy of a signal interference not zero, they are coherent signals. In theory, they cannot coexist in one communication media or propagation media. In reality, if we should analyze spectral density of this energy, we will see some level where this energy is neglectable. So, starting from this point, we can start next data or audio or video something channel. Wait one moment, I would like to show one thing. I have a bit of time. Remember my analyzer of spectral frequency characteristics. What? Source of saw-like signal, it controls generator, switch generator, then this is AGC control circuit, object under investigation, and I can draw a research figure, amplifier with absolute. So, it was my analysis of border plots for some circuits. It has one feature. I can add where, if I remember, I can add here signal from outer generator. It was intended to calibrate frequency scale of this generator, but it also yields us one interesting effect. One moment. Question where to put it. Free some space. free space for my analyzer. Need this space. My nice resonant stays. Oh. Moment. Oh. Okay, what do we see? At this moment, it's simple amplitude frequency characteristic of resonance content. You can see, can you see it?
Yeah.
Okay? So I have this simple parallel resonance content analyzed in frequency space. I need more signals. More signals to the god of signals. 44 kilograms of tiny generator. This monster is a harmonic signal. It can produce harmonic and pulse modulate. At this moment we don't need any pulse modulation. I hope it's work. I hope nothing broken. I can take this nice cable. And attach it to external generate. Okay, this is okay, this is okay. One nothing. Oh. Okay, it operates. Now, can you see this kind of disturbance on characteristic? Oops. Maybe I can. Oh, see this? It moves up at the top. See, something goes on characteristic, like a small tick. You see this tick moves?
Yeah.
This tick is a point when slip generator frequency is near or let's say equal with this large generator frequency. So this at this moment, where am I? 24. For example, now this point is 24 megahertz. Going here, 25, now 28. So this point is 28 megahertz. This thing is designed to analyze spectral characteristics. See, I'm changing frequency and I see a nice tick mark. Oh, now here it sits on 20. 22, 24. Oh, my tick mark is on 24 megahertz. Yeah, it's a tick mark, it's good to analyze. Now, I'll do one thing. I will try to show it in details. How to say, zoom in. One moment, where are you? I'm zooming in my tick mark. One moment. Okay, tick mark, where are you? I would like to see you, for example, here. Can you appear? One more. And more. Okay, here it is. Can you see it now?
Yeah.
See this? Kind of shape we like a butterfly. It is a result in frequency. Here, scale is frequency. It's a result of coupling between internal generator of body plotter or amplitude frequency characteristic analyzer and point and signal from this generator, outer. Actually, it's a mutual coupling. If we take GM, this mutual energy, by frequency, not integrated, but as a spectral density, we will see this. In reality, maybe, no, can I, maybe I shift it here. One moment, I'll try to, here. Tick mark. Come on. This tick mark we see, this green one, is actual coupling. Or better say interference. It's a result of interference between harmonic signal of this generator and harmonic signal of internal generator of it's a slip generator. It's close to harmonic. That's how it looks in frequency space. The only moment it should produce something at DC, but this system is not. It's not good to pass DC signals because it's there's a resonance. We see if I change scale. Sorry, wrong knob. I need this one. Here, in different scale, peak mark sits near the peak of frequency characteristic. But if I zoom it in, if I expand it, we see a real coupling effect between two harmonic sources. Nice peak mark. A moment, I will get it as big as possible. Here. Here it is a nice scale. That's how interference between two harmonic signals looks in when we try to analyze it in frequency. Okay, my time, and but you saw it. Okay, I'm finishing for today. Next time I will try to speak on amplitude modulation. How can we